Now we're going to look at some actual geological formations where oil may be found. Previously, I described geological formations that geologists look for when searching for oil. Within these layers of rock that extend over a large area, structures develop. A structure is a distortion of a rock formation. Let's go back to divergent, convergent, and transform plate margin movement. These different movements cause crustal deformation. The Earth's crust bends or breaks. The energy released by these movements puts the crust under such stress that it bends or breaks. This is how rock structures are formed. There are three types of geological structures: joints, faults, folds. We find oil in all three. Joints are nothing but fractures or cracks. Sometimes, when a rock is under high stress, it starts to crack and causes a change in the rock characteristics. Faults are caused when the rock breaks and moves away or apart relative to the other side. They are caused by stress created by the movement of the plate margins. With joints, the rock formation and shape does not change, it merely cracks. In faults, however, there is a change in the formation and shape. This is caused when the rock breaks and moves. We have three different types of faults. In faults caused by divergent and convergent plate margin movement, you can have high dip or low dip. Dip refers to the angle of the fault plane relative to the horizontal plane. In the faults caused by transform, they move sideways or lateral. These faults have two sides. We identify the different sides by naming them the hanging wall and the foot wall. The hanging wall is above the fault line or on top of the angle, and the foot wall is below the fault line or below the angle. Hanging wall and foot wall are names that come from early miners looking for gold long ago. Since minerals, including gold, is found in faults, the miners dug down to the fault and moved across it, extracting the gold. The side where they hung the light or lantern was called the hanging wall, and the side where they stood was called the foot wall, where you put your feet. These expressions are now standard geological terms. The movement of the fault can be measured in the x direction, right or left. This is called the heave. When the movement is measured in the y direction, up and down, we call that movement the throw. To measure the left or right movement, we measure the heave. To measure the up or down movement, we measure the throw. A normal fault is caused by divergent plate margin movement. Remember, divergent means pulling apart. You might also hear words like extension or tension, but they all mean divergent. These faults can range in size from a few centimeters to many kilometers. In a normal fault, the hanging wall goes down. Its fault plane cuts through the hanging wall and the foot wall at the dip angle. Here you can see they are whitened to illustrate their heave and throw movements. Geologists use sound waves called seismograms to measure the location and types of faults. This is an example of a seismogram. If you look closely, you can see faults. Here's the hanging wall. This one went down and this one went up. So when we see a hanging wall, we know some kind of distortion, some kind of extension happened. It pulled apart. The second type of fault is caused by convergent plate margin movement. It is called a reverse fault. During the formation of this fault, the plate margins were pushed together or compressed. Now the hanging wall goes up. Reverse faults are always formed under compression. The fault plane causes the hanging wall to go up. This is the reverse of a normal fault where the extension forces it to go down. Within reverse faults, we have two types. They are called reverse fault and thrust fault. The only difference between these two kinds of reverse faults is between the dip angles. The high angle, greater than 30 degrees, is called a reverse fault, and a low angle, less than 30 degrees, is called a thrust fault. Some low angle thrust faults can literally be zero, which is what you see here. Divergent and convergent plate margin movements cause normal and reverse faults. Transform plate margin movements causes strike-slip faults. When the whole plate moves, it is called a transform. But when there is movement on only a small segment, from a couple of kilometers to a few meters, we call these strike-slip faults. There are two types of strike-slip faults. Strike-slip left, where the movement is to the left, and strike-slip right, where the movement is to the right. So how do we tell the difference? Let's say you are standing next to this telephone pole on the slide. When you feel the earthquake, you look across the fault to the other side. If it all moves to the right, it is a right strike-slip fault. If everything moves to the left, it is called a left strike-slip fault. With left or right, it doesn't matter which side you are on. The movement will always be left or right relative to your position. Which side is actually moving? We don't always know. They are moving relative to each other. You might be on the one that's moving, or you could be standing still. The opposite side moves right from where you are standing, then it is a right strike-slip fault. The third structural deformation is called folds. Folds are bent planar structures caused by ductile deformation. Ductile means something you can bend and then it will hold its new shape. Copper wire is an example of ductile deformation. You can bend it and it will stay in the new shape. Remember, ductile means that it bends. It doesn't break into two or more pieces. Surprisingly, under enough heat and pressure, rocks will bend. Rock folds that are formed where the center goes up are called anticline folds. Where the center folds down, we call these syncline folds. Oil is found only in the anticline folds. Here is an example of an anticline. The flanks are bent downward, forcing older rocks up to fill the inside of the fold. In syncline folds, the flanks bend upward, pushing against older rocks on the outside. We never find oil in a syncline. If you look at an anticline fold, you can see here where the oil can get trapped. It accumulates up into this area beneath the fold. If the cap rock is impermeable, then it gets trapped. Anticline folds can run from a few millimeters to tens of kilometers long. In the big oil fields, these underground anticlines run for kilometers and are very large structures. Here is an example of a simple, symmetrical anticline, but nature does not always give us symmetrical structures. There are three other types: asymmetrical anticline, angular anticline, and plunging anticline. When something has occurred to make the two sides different, then we refer to these anticlines as asymmetrical, meaning one side is different than the other. In this example, you can see that one side is far more bent than the other side. This is an angular anticline. The top of the fold makes a sharp angle. It is not rounded like in a symmetrical anticline. Something violent happened here to twist the structure. It did not break, so it still can be called a fold. Another type of anticline is a plunging anticline. Sometimes, when mountains are formed by uplifting forces, they are pushed up. This mountaintop is a sharp anticline structure. It got pushed up. Everything else fell down around it. In this model, we see examples of anticline and syncline. Many times they appear together. The area where the anticline structure runs into a syncline structure is called a limb. The hinge line is the maximum point at the top of the anticline. It runs parallel to the top of the curve. This line is important because it shows closure, a place to hold oil. This concludes Chapter 1. We've talked about how the Earth was formed, the theory of plate tectonics, the internal divisions of the Earth, and its geological structures. It is important for us in the oil industry to understand how the Earth's formations and structures were formed. We can then apply this knowledge to help us locate oil fields and better develop existing ones.